I think we are. Okay. So the strong nuclear force. What did we talk about last week? Does anyone remember what the strong nuclear force does in an atom? Max?
It holds the nucleus together.
It holds the nucleus together. Why does the nucleus need a force holding it together? Go ahead.
Because there's neutrons that have no charge, and then the only other part of the nucleus is the protons, which have a positive charge, so they naturally kind of repel each other. So they need something to hold them together without just coming apart.
Exactly. Like charges repel, there's no reason that a bunch of positively charged particles would like to be packed into close proximity with each other. So it takes a huge amount of force to hold them together, and that's the strong nuclear force. Strongest force in creation. Ooh, there's a horrible glare. So, how does the strong nuclear force work, do we think? Bethany?
Exchange pions.
Exchange of particles called pions. And what do we know about pions?
Very short-lived.
Short-lived. Okay, so what does that imply about the particles that are exchanging them?
That the particles have to be close and that the exchange has to be quite fast, otherwise they'll die on the way, in a way.
Right, so if you have to exchange a particle that exists for like a meep of a nanosecond, you need to be very close to the thing you're giving it to or getting it from. So when you have this fast particle exchange, then to hold the nucleus together, the particles have to be very close together, which is what we observe about the nucleus. So that works. And other topic we have to talk about this week is nuclear decay. So when you have an isotope of a particular element that has the wrong, I guess, number of neutrons, you have an unstable nucleus. Some isotopes are unstable because of the not normal number of neutrons. So what will happen in that situation? Joshua?
The atom will try to lose neutrons through alpha, beta, and gamma.
Okay, so we have three kinds of decay, alpha, beta, and gamma. And my old brain needs to look. Well, maybe it will write on the board. So tell me about whichever of those is your favorite, if you'd like, or someone else can.
I'll talk about the energy reactor.
Go ahead.
Okay, gamma decay is basically when the atom releases energy. Gamma
All right. Does the element change?
No.
Does the mass number change?
No.
No. What changes?
It just loses energy.
Loses energy. So, go ahead, Chris.
I thought it was like the nucleus change, or was that different?
No.
That's a different kind of decay. The other two do.
Can I go back?
Sure. So when you have gamma decay, you have a nucleus that's releasing energy. Now, how dangerous is this type of radiation? Because all nuclear decay produces radiation. How dangerous is this for you, Max?
Very dangerous.
This is the bad stuff. And what do you need to protect yourself from gamma radiation? Joshua?
You need very thick lead.
Thick lead, okay?
All over.
Yeah. You want to be in a lead box. You need thick less PB, in case you're interested in the chemical symbol for that. Who would like to talk about alpha or beta? Max?
Beta decay is when it actually changes a neutron into a proton.
Well, how does that happen?
I think I'm not sure. Oh, somehow it picks up a positive charge.
Okay, well, what does it lose?
It loses an electron.
Okay, so
electron.
beta decay is a neutron emitting an electron and becoming a proton. So a neutron, neutral charge, right, emits an electron and becomes a proton. That's super simplified. But you know that the electron and the proton have equal and opposite charges as exactly far as what we can measure them. So when you lose the electron's negative charge, it's like negative 1.6 times 10 to the negative 19 coulombs or some charge like that. I think that's it. And then, you know, if you've lost that much negative charge, then the thing left behind must have that much positive charge. And so that is a proton. And you know that the neutron is the tiniest bit more massive than the proton, right?
Yes.
Right. Okay, so is this dangerous?
No. Yes.
No or yes. No or yes, you know. So what is it emitting?
Electrons.
An electron. And what do you think will happen to that electron?
It gets put in orbit.
Yes, because now have we changed into a new element?
Yes.
Okay, if you have one more proton in your nucleus, right, let's say, well, here's somebody that does, let's look at carbon, right? If you have a carbon atom that undergoes beta decay, it has 6 protons. When one neutron decays into a proton, now it has 7 protons. Now it's nitrogen. So it becomes a whole new element. And that new element is one mass, or one atomic number higher on the periodic table. Okay, so then, what's the other kind of decay? And what's the other color?
Monofusation.
Yes. Other kind of decay?
You do
Well,
one.
what type of
Oh, what do we need?
what
You're
do
right.
they use in microwaves for?
Microwave is like, you know how there's visible light? And there's like ultraviolet and infrared. I'm talking, my skirt is like, yeah. You can see one patch of my skirt. Maybe it'll be the patch that I dipped in acid today. But it's a type of electromagnetic radiation. So it's light waves. It's not decay radiation.
Because there are
It's
some
just-
myths that if you stand too close to a microwave, it can damage you.
It is electromagnetic radiation. So like ultraviolet will damage your skin, you get a sunburn. Microwave does a different kind of damage, but it is an electromagnetic wave just like light. And these guys are, gamma is an electromagnetic wave that has an even shorter wavelength than purple end, right? Heat, infrared, has a bigger wavelength than red. So like if you look at the electromagnetic spectrum, visible light, all of the other stuff, gamma is way out here, microwave is somewhere down here. What have we not? Oh, I know what it was. We did not talk about what you need to protect yourself from beta decay. So, when this happens, when a neutron loses an electron and becomes a proton, guess what else it does? You're saying?
It releases energy.
And what do you need to protect yourself from that?
A thin piece of metal.
Okay, so it can release energy. You need a thin layer of metal to protect yourself from that. So it's also dangerous, even though it seems like giving off an electron is no big deal, right? That when you have one extra proton, you're now nitrogen, well, you would also need one extra electron, right? So hooray, all good, not dangerous, but that's not true. It's going to give off also energy, which is dangerous for you. Do you see?
The beta decay also lets out that little
Anti-neutrino?
Yes. What is that?
Yeah.
No. And where is
I don't know what, I don't even have any concept of this. I took 2 semesters of this stuff, and every word she said was just like, not my field.
It's like she watches this video. just like-
Please go watch MIT Physics if you want a third year MIT Physics if you want the truth. I've got absolutely no way to simplify that nightmare for you. Sorry. And you know, all of that stuff is fairly new research. Like these subatomic particles are cutting edge science, and they're really cool. And I shouldn't have written that in green, man. But anyhow, who would like to tell us about alpha decay? Who have I not talked to? Elise. What's alpha decay?
It emits 2 electrons.
Okay, so we emit 2 electrons. I have to look because my brain is. Okay, 2 what?
Electron.
No.
Neutrons.
And okay, so this is when a nucleus emits 2 neutrons and 2 protons. So what exactly is that, Joshua? It's a helium nucleus. So if you look here, 2 protons, anything that has 2 protons is actually a helium nucleus. And the average mass of a helium nucleus is 4.00. So that means if it has 2 protons, it also has 2 neutrons. So this 2 neutron, 2 proton combination is a helium nucleus. Yeah, nucleus, I promise. He, a helium nucleus. So alpha radiation, alpha decay emits 2 neutrons and 2 protons. And is this dangerous? What do you need to protect yourself?
A piece of paper.
A piece of paper will protect you. That's true. So when it comes to being able to pass through matter, right, the energy can pass through metal or even thick lead. But, I mean, 2 neutrons and 2 protons, though unbelievably small in the grand scheme of things, do have a size and a mass, and so they don't even really readily pass through a piece of paper. So that would protect you from that. So those are the 3 kinds of radiation. So if you grab last week's bean worksheet, we'll decide what would happen to a nucleus that undergoes these kinds of decay.